Ladies and gentlemen, please welcome to the stage Leif Peterson, Biovia CEO.
Now we're going to jump on to a presentation by Dr. Bruno Ferré. He is one of those drivers of the Industrial Revolution. He does this by decreasing the distance and improving the capacity of knowledge and know-how through his work of bridging the virtual and the real. So every day, Dr. Ferré is an orthopedic surgeon at the Medical Institute in Monaco. And besides that, he heads the informatics department the same place. And by bridging the work and doing both the practical side as well as the technology side, he's been able to build simulations and other models that will help drive personalized medicines and some of the outcomes we're going to go see. High energy, a lot of work has gone into this work. So it's with great pleasure I introduce Dr. Ferré. Please welcome on.
Thank you very much. I'm Dr. Ferré, orthopedic surgeon, and I'm very honored to speak in front of you today. I will try to show you how digitalization, which has revolutionized many professions, will profoundly modify the practice of medicine by improving the efficiency of our diagnosis and our treatments. Modelization will occupy a prominent place in this revolution. Sooner or later, we will all be confronted with disease and the consequent anxieties. Depending on whether we are the doctor or the patient, the disease will ask us these questions. If we are the patient, our anxiety centers around the diagnosis and the correct treatment offered. If we are the doctor, we would like to be sure that the treatment that we offer to our patient is the right one and will not be followed by complications. We want to predict failure and not face it inside. Man has always tried to answer this question with the means at his disposal. In ancient times, our ancestors tried to answer this question by going to consult the goat and oracles, or making sacrifices to try to coax these same gods. Things have fortunately changed, and medicine is currently based on evidence. After a doctor examines a patient, he or she puts forward a hypothesis that will be tested with complementary examinations. Then offers the patient treatments by considering advantages and disadvantages. And finally, the doctor will administer the treatment with the hope that the choice was correct and the expected result will follow. With this method, facing the patient who wants to heal, the doctor alone makes the diagnosis and treatment, applying his or her disparate books, video, congress, etc., knowledge and experience acquired over the year of practice and study. It is a process that depends heavily on the physician alone with his limited knowledge. The effectiveness of such a method is not absolute and leads to increased cost and mistake. The digital revolution will make it possible for the doctor to feel less isolated with his patient and make more effective decisions. For diagnosis, decision support systems, CDSS, will allow algorithms to help the doctor with diagnosis and treatment proposal. The doctor will be able to rely on all the techniques of digital simulation. This will help him to choose the treatment and to be able to foresee his eventual failures. This is what we will highlight in this presentation. Finally, and this is our main point, all the data produced during this process will be saved. This will allow the extraction of correlations from the data analysis that will in turn allow us to enrich our knowledge and therefore our effectiveness with patients. I will now show you how we have been able to develop effective orthopedic surgical modeling with Dassault system application. Why don't we need modeling? Because our results are not always good. The literature shows that surgeons who specialize in heavy ankle surgery report 15% of poor results, while the literature also shows that the patients were only satisfied in 50% of cases. Why so much failure? Let's take an example, a case of osteoarthritis of the ankle. Osteoarthritis results from the wear of cartilage, which is the sliding surface between the two bones, which is sometimes explained by anomalies of the geometry of the joints. In this case, the image is full weight bearing, shows the disappearance of cartilage between the ankle bones. CT arthrography demonstrates the focal cartilaginous abrasion of the lateral sector of the tibial-tabaral joint. MRI shows the subchondral osteomedullary changes and cartilage wear. By demonstrating on static images that the ankle is off-axis, we deduce that this enables to realign the system by removing a bone wedge or by translating the lower part of the calcaneum to heal the patient. It sometimes happens that despite an appropriate geometric correction, we have unexpected defects and poor results, sometimes with worsening of the lesions. Our reasoning is therefore unreliable because it does not take into account the complexity of the biomechanical model of force creation during walking. Today, it's possible to predict the result of an experimental crash test. Why not predict the result of a surgery before going to the operative room? Are we doing the right surgery? To model our intervention, we must reproduce the functioning of joints whose axes are never parallel to each other and never perpendicular to the line of displacement. And the hip joint has an axis which is not fixed and which changes position during movement. To simulate this function, we must reproduce the complexity of the joint, where the movement is controlled by the complex form of bone, where the joints don't have the perfection of mechanical joints and have irregular shapes and surfaces. You can see here that the articulation between the tibia and the astragalus is a truncated cone, and that the surfaces in contact are very irregular. The slippage between the two bones is produced by the cartilage, which is a fabric with very special properties and which is lubricated at very low speed. In addition, the joints are functionally linked in a kinematic chain that is very joint play movement to allow them to adapt to the constraints of walking on uneven ground. The bones are fixed together in a static and dynamic way. Static fixation comes from ligaments that fix the bone to each other from the outside. During movement, only a portion of the ligament is stretched, the rest extend relax. This allows to variation of the axis of rotation and explains the joint play movement. Dynamic assembly is made of two elements, the plantar plates and the muscle via the tendon. The plantar fascia and the plantar plates bind the front and the rear foot and press the toes to the ground during the support. The tendons that are connected to the muscle are active elements. Their role is to lock the joints of the foot to turn it into a rigid body capable of supporting the propulsive force produced during walking without breaking up. The tendons are directly on the bone by attaching themselves to them. Finally, tendons surround the bone where they have the same effect as a rope on a pulley, and indirectly by acting remotely when acting on straps that are attached to the bone. To complete the model, it's finally essential to model the structures of transmission of forces on the ground, the L pad and the plantar pad. In this complete model that we test, comparing it to our living model to validating. In SIMPAC and Abacus, users obtain a behavior of the virtual foot equivalent to those of the real foot. The curves of the ground pressures and kinematics are the same. We know how to build a generic model. I will now show you how we use CATIA, SIMPAC, Abacus, and ISA to customize this foot and ankle model by performing a biomechanical foot clone for each of our patients. The only thing we can easily get from each patient is his bone geometry from the medical scan data. which allow us to obtain 2D images of fine slices made at the level of the foot and ankle. The series of 2D images in DICOM format must be processed and reassembled in order to obtain a 3D image in STL format by an operation that we call segmentation. These STL images that are just cloud of points are imported into the CATIA application where these different modules allow them to be transformed into a surfaces to a real mathematical objects that will enable us to carry out all modeling operations. From this patient-bound geometry, thanks to the automatism and the language of CATIA, we will add the soft parts. First, the cartilages, then the ligaments, and finally, the tendons. This patient-specific model is then imported into SIMPAC, allowing us to determine the best muscle activation pattern through clinical data from the CDSS. We can then pass the model into Abacus to study the constraints that interest us, between the bone on the rear foot, between the foot and the ground in the forefoot. This allows us to highlight the abnormal constraints that explain the disorder in this patient. We can then perform a virtual operation. For that, we modify in CATIA the geometry of the patient's foot and check in Abacus that the constraint and improve. Unlike all other preoperative planning methods, this technique is the only one to allow an overall modification of the geometry. As you can see here, a simple osteotomy modifies the whole mechanics because it changes all the levers at the points of implantation of tendon and ligament. It is this modification of the global geometry that will be reinjected in Abacus to verify that the constraints are really improved. Taking again the example of the ankle osteoarthritis from the beginning of our presentation, you can see here the changes brought by sectioning on the tibia to correct the axis, which causes, at the level of the ankle joint, a transfer to the stresses on the lateral side. We use eyesight, which allows us to automatically test a therapeutic hypothesis so that we can choose the best solution between the amount of displacement and its direction. We have also developed surgical intervention libraries that are easily applied to geometry thanks to the automation system contained in CATIA. We can thus deliver to the surgeon to help him in his treatment of some implantation schemes with a lot of bone as manufactured by additive printing, surgical robot piloting scripts to help implant prosthesists, even made to measure medical device with the piloting software to implant them. In conclusion, with this method adapted from that use from the development of airplane, we can go from a surgery where we was a failure to one where we avoid it by anticipating it. Finally, and this is extremely important, we record all the information that is generated during the analysis in order to be able to improve the efficiency of the system by comparing the modeling data with the pre- and post-operative clinical data. It must be possible to use this method for all orthopedic surgery. We need to solve a number of problems. We must first automate bone recognition. Initially, each bone is only one part among others. To integrate them into the surgical reasoning, the machine must be able to recognize them automatically and give them the name used by surgeon. This requires the development of particular algorithm. This task is very complex because of the diversity of anatomical forms. Take the example of the astragalus, which is the central bone of the ankle. You can see on the bone of patients polymorphism from that can sometimes be extreme, as in these two deformed talus due to trauma. Algorithms can help us, but they are limited to set case. For the bone recognition to be 100% reliable, we must implement machine learning systems that include all data of our patients. We will then be able, with the algorithm and the analysis of our data, to adapt the cartilage, tendon, and ligaments to the bone of each patient. Each complete model can be stored in the database. It will enrich the possibilities of recognitions and automatic reconstruction of patient models in a process that will allow to pass directly from the scanner to Abacus. Finally, and this is essential, using Enovia application, we will be able to stock and analyze the totality of the data of each patient to extract new knowledge to improve care. Let's now talk about the problem we have encountered and our prospects. The first problem is storage and the amount of data we generate. This causes storage difficulties in the cloud and increased computing time. The second problem is the adaptation of the application we use to life science. These apps have been developed for industry where 2 plus 2 still equals 4. However, due to vast complexity of biomechanics, where we use this application, 2 plus 2 is equal to 4 plus or minus delta. The first limitation is the transition from 2D to 3D by the segmentation that is currently done by third-party software. It will be necessary to recover the data directly at the source of the CT scan to subsequently inject information as mathematical object directly in CATIA without going through the DICOM format. We also encounter problem when converting STL to CATIA surfaces, because the biological surfaces are irregular and complex, which forces us to use very fine resolutions in CATIA on the nanometer order to be able to pass our geometries directly in Abacus. We have trouble defining the properties of materials correctly, which sometimes cause problems of numerical instability in Abacus. The properties of living material are poorly documented and seem too approximate when we test them in Abacus. The solution, no doubt, is to pass from implicit mode of Abacus to the explicit mode. The modeling of cartilage gives us problem because it is a very particular material which is lubricated at low speed. We need to construct a reliable model finding compromises between and among geometry, meshing, and mechanical constants. Communication between applications is sometimes complicated because the scripting language are not the same. Communication channels are signed even when applications are in their Power BI versions. These problems will be fully resolved when everything is on the cloud. We are very optimistic because these difficulties have not yet been tackled by the R&D teams. We, given their quality and their motivation, will be able to solve them quickly. We know how to model orthopedic mechanical pathologies. The biggest challenge will be to model knowledge. We must know how to create a system centered on the patient, where we can, in real time, pilot the mechanical modeling on our treatment directly from the clinical data. For this, we must computerize a medical approach, which is only one intellectual approach among others. In simply use our deduction capabilities, algorithms, and our experience, our big data. For powerful computers to help us, we need to structure our knowledge so that it can be exploited. This is easy when it comes to discrete digital or objective data. It's a lot more complicated when it comes to continuous subjective data. This is the case of clinical data, which in medicine represents the keystone of our reasoning. And we must define for each clinical thing, the semiology, an input grade that will make the clinical data reliable. We must ensure the quality and relevance of this clinical data. It is therefore necessary that each medical field experts validate this knowledge. This knowledge must finally be structured. It must evolve easily thanks to the analysis of massive data generated by its use, by quickly transversed by the algorithm. Only when this validation and structuring works is done, will users be able to get help from the system and test personalized treatment before offering them to their patients. Finally, all data created during this use will be stored in an additional database, so that they can be analyzed by medical experts. Data scientists must intervene to improve the knowledge base and to create new knowledge by growing data of all kinds, image, text, video, etc. We will have to achieve the best result explore the storage of unstructured data and use artificial intelligence through dedicated medical-driven industry solution experiences. Finally, we must find solutions to push the limit created by the collection of clinical data that is very complex to analyze and which are the weak point of our procedure. We are, of course, only at the beginning of the digital revolution of medical thought. We are barely able to model the pathology of the foot and ankle. I can nevertheless assure you, after having put in thousands of hip and knee prostheses before devoting myself exclusively to the foot and ankle, this approach can apply to all orthopedic surgery. Nevertheless, if we want to create real personalized and predictive medicine, it will be necessary to integrate analysis derived from genetic model and control system of homeostasis. All this will be only one step in the overall understanding of the patient. We will have to integrate the modeling of the brain and its psychological component. Finally, we all know that man is only one species among many, and that will not be able to understand how a human works without understanding how the world of life works. And that we need to understand the world in which we live, which will lead us to realize that it is fragile and must be preserved. Conclusion, I will let each of you reflect on the negative aspects of this approach, and I will limit myself to being optimistic and believing in humankind. In the first place, such system will enable us to improve our ability to increase in knowledge. It's our duty. It must also, above all, allow us to devote more time to our patients by increasing our humanism, and above all, to be more attentive to our patients by increasing our compassion for them. Thank you very much.